In earlier videos, I've talked a little bit about energy and its relationship to stability, and I'd like to formalize some of our treatment here in this video. Our learning goals in this case are going to be how we use standard heats of formation to assess that relative stability, especially if we're comparing similar molecules. Now, what is that relationship between stability and energy? Let's talk about that a little bit. Systems tend to minimize their energy. Lower energy systems then are thought to be more stable because that's where systems go spontaneously. Now, it turns out there's more to spontaneity than just lowering the energy, but that drives a lot of the processes that we observe in chemistry. When we minimize energy content, it often drives that spontaneity. So when we look at a chemical reaction, for example, part of what often drives that chemical reaction is that the atoms are trying to find a lower energy state in which to occupy. But it's also true in a number of other processes in the world. So what does this look like diagrammatically? Well, if energy is a vertical axis, we might have two possible energies for a system, and the one that is more stable is going to be the lower one, and the one that is less stable, the upper one. So you might think of this as analogously, it takes energy to climb out of a hole. Laying down in the bottom of the hole is a pretty stable place to be, whereas if you're up on top of a mountain, it's not a very stable place because if you slip and fall, you're going to fall all the way down. We need a reliable way of determining this for different kinds of compounds. So what we're looking for is something that enables us to assess this relative stability based on energy considerations. To do this, we're going to use reference states. All right, so what I want to ultimately get out of this is the ability to compare the relative stability of two different molecules using a common reference. Okay, one analogy for this might be how we use sea level as a reference for altitude. So, for example, if we want to determine, what object is at a higher altitude, we would measure its altitude relative to sea level, and then we could compare them. And by comparing them that way, we could determine which one is higher. So that's how we know that Mount Everest is the highest point on Earth, because we can measure its height relative to sea level and see that it is higher above sea level than anything else. For molecules, what we use as a reference is their most stable state at room temperature and basically atmospheric pressure. This forms the reference state for them. And to give you an example, for carbon and hydrogen, the reference states would be for carbon, it would be the graphite, which is the most stable form of carbon at room temperature and pressure. And for hydrogen, it's diatomic hydrogen. All right, so these are forming a reference state. Now let's suppose I've got here the reference set of 2 carbon atoms and a total of 6 hydrogen atoms. There's a couple of different ways that I could manipulate this set of atoms to create some different outcomes. So for example, on one hand, I could make 1 carbon-carbon bond and then fill in 6 carbon-hydrogen bonds. Or on the other hand, I could make a carbon-carbon double bond, fill in 4 carbon-hydrogen single bonds, and leave 1 hydrogen-hydrogen single bond alone. Okay, in the first case, the thing I'm going to create is ethane molecule, 1 carbon-carbon bond and 6 carbon-hydrogen bonds. In the other case, the thing I'm going to create is a molecule of ethylene with a molecule of hydrogen. All right, so these are 2 different outcomes that came from the same set of 6 atoms. I can compare their relative stability now because I have a reference state against which I can compare them. So if I compare how I go from the middle part, the collection of atoms and elements at their reference set, to each of these outcomes, I can now determine the relative stability or the relative energy of these 2 outcomes. So here is where we're going to introduce a new piece of data that can be tabulated, and that is the standard heats of formation. So what we're going to do is for each compound, we're going to establish its energy relative to this reference standard. Okay, that energy relative to the reference standard is something we call the heats of formation. And since the standard is measured at standard temperature and pressure conditions, we call these standard heats of formation. We give it a symbol, delta H sub F. The F stands for formation. The little degree sign indicates that we're using standard conditions. The H actually stands for something called enthalpy, and we'll learn more about that in the next course. But you can think of enthalpy as a form of heat, and it's the form of heat that's particularly relevant for molecules, especially under constant temperature and pressure conditions. The delta is the difference in the energy content of these systems relative to the reference standard. We typically report these standard heats of formation in units of kilojoules, that's 10 to the third joules, per mole, that is per 6 times 10 to the 23rd molecules. So it has a value that we can measure in a laboratory. Obviously we don't count all those molecules, but we can determine how many moles there are of molecules in other ways. These values give us a yardstick for determining the energy content of molecules relative to one another. So they're a very useful tool for determining this relative stability because we have these tabulated and we can compare any two molecules that are created in this way. Where can you find these values? Well, practically most textbooks have some of these values, but the most authoritative source you can go to is this site on the web called the NIST Webbook. And this is the URL for that site. At some point, perhaps we'll do a video showing how to explore that site and get useful information from it. But you can essentially look up any chemical compound on that site, and if somebody has measured the heat of formation for that compound, you can find it. I hope this has been helpful, and we're going to be using some of these concepts in the lessons to come to discuss these very issues of energy and stability.